Well, it's the physics video lecture once again. This is Physics 105A video lecture 29, and we're in some really great material now. Heading towards the central force problem, but we still have a little bit of technical work to do with some of our integrations, line integrals for instance. Let's start by reviewing where we are right now. We're doing motion of a point particle in space. So there's Newton's law in its generality. But we talked about a couple of examples, and now this is a vector R. And then we went from this general, or some examples of this, to the specific case where the force is a function of position only. So we had this, we did some examples. Now we're talking about force is a function of position. And in that case, you can define a potential energy function as this line integral of the force. Not so fast. That's an R prime because it's an integration variable dotted into dr prime. So that's an integral that ends up at the point R where we're measuring the potential energy. So if we have something like this, and we learned last time for which the curl of our vector field equals 0, then we legitimately have the conservation of energy. So then 1/2 m velocity squared plus u equals E equals a constant. And as was the case before, this is a first order differential equation as opposed to a second order differential equation. So when you have this kind of conservation law, you make use of it. Okay, let's put that in a box. So we had conservation of energy. And yeah, there are some interesting technical aspects of doing this type of integral. So that's what I'm going to revisit now for a moment before we continue on. So this type of integral, yeah. And let me put one more thing here. So curl of F, curl of that vector field vanishing, that force vector vanishing, is necessary and sufficient. The connection that I want to make here explicitly is that the gradient of u of r, so gradient of u of r is equal to minus f of r. That's really key, of course, and we made use of it in that proof, and we actually showed this when we were doing the general theorem for these line integrals here. The general fundamental theorem of calculus for these line integrals, which we had up there on the board the other day. So yeah, we have all of these things fair and square. Let's spend a little more time on integrals of this type. And there's an interesting application we'll do with our cycloid. And now we have that cycloid. So integration. We'll return to the vector integral theorems probably next semester, where they play more of a role. I didn't write down the divergence theorem, we'll get to that as well. But yeah, let's look at this thing here. Once again, we'll just do it in a general sense. So we have f of, well, we'll call it capital F. F of R dotted into dr. So that's just symbolic. You might say if we wanted to do a concrete integral, we would have to find or have a parametrization of the curve that goes from A to R. This is R prime again, okay? We need a parametrization because this is actually a curve in space, okay? There's R, there's A, we start here, and we end up there. So that parametrization, as we saw, it was an R of tau, okay? So it was a vector R of tau, and since I have this, I guess I have to keep calling this R prime of tau. Okay. And then our dr there, we're dotting into a dr d tau, and since this is tau, okay, it's not time, so it's not necessarily a velocity vector, but it has the same properties as a velocity vector, namely it's tangent everywhere to the curve by definition, by construction, as we learned in kinematics. So then we integrate that over d tau, and then that's a tau sub A and a tau sub B. And that R prime of tau sub B is right there at our endpoint. Okay. So that's how we do integrations like that. And I'm going to give an example. Namely, our cycloid. So that cycloid's a very interesting curve. We just generated it the other day out of a rolling wheel. And let's go ahead and remind ourselves, we'll just call it R, and it'll be a two-dimensional vector. So we're in the XY plane like this, and we remember we were rolling it forward like that. So what did we have? We had R theta minus, in fact, let's leave a little room here. I have R of theta, and it's a two-component vector. So I have this radius theta minus R sine of theta, and I have R minus R cosine of theta. So this is a parametrization of that cycloid, and instead of tau, the natural parameters, what's in a name? Tau is just a name. Here it's the actual angle theta when we were rolling the thing forward. So if we had a field in here, so that's R of theta, and we're just going to take our simplest field, F, in this case, is simply going to be minus M, or M times G. M times G, that's a constant field. So what would that be here? M, that would be 0. We're going to have G in the vertical direction. So that would be 0 and then minus mg. So that's that vector. And if we had to do an integration with the dot product of this, so it would be the dot product of f dotted into dr d tau, right? So what are we looking for here? Dr d theta. Is going to be R minus r cos theta, and then r sine theta. So there's my vector, there's my f of r of tau, just that constant vector here, and there's the dr d theta, and I'll integrate it up with a d theta. So now what do we have? Integral f dot dr d theta. That's a real dot product d theta. So the dot product is going to have minus mg and the r sine theta. Right? This one gives a 0. D theta. And yeah, obviously if we went from 0 to 2 pi, we would have gone through this thing in its entirety. Sine theta from 0 to 2 pi 4 is going to integrate up to 0. So I'll leave the boundaries empty. You can do what you want with that, but that's an example of a line integral, and because it's a dot product, of course, it's just a projection onto the y-axis. Now here's a related integration. So next, a related integration is the length of a curve, and since we have our cycloid up here, let's do the length of the cycloid. This one I'm going to assign as homework. And it's really interesting because this cycloid is rolled out. So we go, here's our theta, and we're going to end up here at 2r. And so it rolls out like that, and this would be 2 pi when you roll out that thing in its completeness there. So this is 2 pi, and what you're going to find when you calculate the length of this thing, it's actually a whole number. Just one of those things that turns out that way. So let's go ahead and say this is a homework problem, but let's set it up. So if we were doing the length of a cycloid, it would be the integral over dl. But what is dl? What's the length element? There are a couple of ways to get this. What we're going to do it as is equals the integral over the magnitude of dr d tau times d tau. Because you can see that is, actually let's do it this way. I skipped a step. And I'll draw a bunch of little dRs, as you know, infinitesimals. They would be like that, right? I'm going to get this expression in a couple of different ways. So the integral of dl to find out what the length is would be a summation, and we'll call it an integral, of a bunch of these little dRs in magnitude. But then we can say, okay, that will have to be these dr over d tau times the d tau. And that'll actually be the length. So what are we going to do for our cycloid? I'll write here the cycloid. There's our dr d tau. So we need the magnitude of this expression. So we're going to go dr d theta, construct the magnitude, right? The square root of the sum of the squares of these two components. Then you're going to be integrating over d theta from 0 to 2 pi. Okay. Now there's a formulation of this that I also want to give. Yeah, this will get you the answer, okay? And this is a quick but legitimate construction, okay? Because we know that these dR's from this type of derivative are tangent to the curve. So in the limit where we go from a sum to an integration, you know, that was symbolically here. We're summing up all of these, and then since those are the magnitude of these little vector elements, you know, multiplied by the parameters summed, this really does it. Let's do, as a note, another example. I'll use that picture up there. This though is homework. You'll be pleased with the result, okay? So this one we're going to call length of a curve. In this case, it's going to be when we have y equals f of x. So this is a restricted version of a parametrization. So this is when we have we've got a single valued function and we have a curve here, right? Y equals f of x like that. So here we can do the following. We can construct a DL just out of our difference quotients. You know, we have dy and dx, and we can say DL is equal to the square root of dx squared plus dy squared. And then we're just working with infinitesimals. We can say it's equal to 1 square root of 1 plus dy over dx squared times dx. And so if you wanted the curve, say here from x of a to x of b, you wanted the length of that curve, you could say L is equal to integral root 1 plus dy over dx squared dx a to b. That'd be a length of the curve as well. Now, are these two formulations related? Or, in fact, they are related and equivalent. I would say this one follows from that more general expression. So I'll just put a note here. Let R of R of x. So if we want x to be a parameter, we can make our vector like this. It's x comma f of x, right? That's our vector, so to speak, with the coordinates x f of x. Right? There's our origin. There's a point, right? X f of x. So in that case, our dr dx vector is 1 comma f prime of x, and then its magnitude, dr dx magnitude, is the root of 1 plus f prime of x squared. Okay. And then we multiply it by dx, d tau, and we derive it right here as well. Okay. So this is also a standard form for the length of a curve if you have a function, a single value. But a parameterization can be a lot richer. You could have, if you're doing a parameterization, you could conceivably, and not only just conceivably, you could literally have it from our most recent homework assignment with the charged particle in the magnetic field. You could have a parameterization that gives you something like this. You can no longer express that as y equals f of x, right? So parameterization is a more general way of describing curves than just the functional form, but they both come give you the same thing. Okay, good. So we have that interesting little problem as homework, the length of the cycloid, give you a chance to review these things. And maybe I should put a word or two here. Yeah. So what this is the parameterization. It's the parameterization of what otherwise would just be a function. Parameterization of the curve. Okay, good. Let me consult the clock now. Okay, so now we're going to continue on with the mechanics. Set this up. So what we started out with today, so back to point mechanics, point particle, we're looking at Newton's law, force that is just a function of position. We know that we have a potential energy F dot dr, I'll just write it this way, and we have conservation of energy on our way to solving this. 1/2 m r dot squared plus u of r equals E. Okay, so that's, and I should say where gradient of u is equal to minus f. Okay, so that's the type of mechanics we're working in, and in particular we're looking for a special type of force here called the central force. Point mechanics, central forces. So what is a central force? Central force we have F of R is equal to F of R times vector R divided by R. So this is a force that's oriented away or towards the center. And the center here is our origin. And this is, of course, just a vector that's directed away from the origin. So if this is the origin, I'll just call it O, and I've got a point out here, then my force, different color, is, get that moment, either directed away from or towards that origin. That's what a central force means. And we should make sure we write this lowercase r is equal to the magnitude, not square root, is equal to the magnitude of our vector. Okay. And since we're in 3 space, that is the square root, x squared plus y squared plus z squared. So this is enormously important. We'll spend plenty of time on this when you study electricity and magnetism. You'll spend a lot more time on all of these central force type of and vector problems of this type here. But what I'm going to do is remind us of that problem we had on our exam the other day. Because we had discovered, I had just written down a kinematics problem essentially, and we had discovered that it's actually a central force. It had this form. So let's go ahead and look at that right now. For our example, let's say example, recall R equals A cos omega t B sine omega t 0. So those are x, y, z components. We had A and B and omega are all positive constants. And what had we learned about this thing? We had learned that x squared over A squared plus y squared over B squared equals 1, so that is an ellipse. This vector traces out an ellipse. Okay. But then we took 2 derivatives. We took one and then we took a second. So what was our second derivative? Well, these are all constants, so it's easy. We ended up with minus omega squared A plus omega t minus omega squared B sine omega t and 0. And we were able to pull out the minus omega squared. So in particular, if we just wrote mr second derivative, which is supposed to be the force, then this is a kinematics problem, but we can identify what that force is, namely minus m omega squared. And if I pull out the minus omega squared, then I'm left with A cos and B sine. I'm left with my original vector R. So apparently that's a central force. And that way we can say this kinematic expression here is the result or the solution to a central force problem. And it's ellipse, it's an ellipse as well. Now therefore I have to hasten to say this elliptical solution to this central force problem is not the Kepler ellipse. Okay? The Kepler problem is our main goal of this section, and this is not a Kepler ellipse, so I'll put that here. Star note. Star is not what I'm going to say, the Kepler ellipse. Because this is going to have a different potential energy, but let's just pursue this some more because we have everything up there on the board. So there's our force, and it's a central force. So next, what is the central force? What's central force and potential? question mark. So what we would be saying is f of r over r is equal to minus m omega squared r. So what is the force and what is the potential energy? What central force and what potential energy? Okay. Well, apparently F of R is equal to minus m omega squared r. You notice this is the function of the magnitude. And this is a this is a vector, but see these vectors are identical there. I can cancel them and the function of the magnitude just cross multiply over. And what about u? Therefore u of r is equal to minus integral f of r dr, the little prime here, and we're going to have a minus times minus plus, let's go ahead and plug that in first. So we got rid of the minus signs already. M omega squared r dr 1/2 m omega squared r squared. Okay, got the positive sign there. And you guys may recognize this. Looks like we can rename this m omega squared to a k, right? This is a spring constant. We've seen this before in one-dimensional oscillations. So I'm just going to go ahead and say equals 1/2 k r squared. So u of r is equal to 1/2 k r squared. And what you're seeing here is a Hooke's law, right? Restoring force proportional to the distance. So you're looking at a Hooke's law. It would be hard to construct this using a spring though, because it's a pure 1/2 k r squared law. There's no relaxed length of the spring in there. Okay, but yeah, it's got the same form as a Hooke's law. And so you can say this potential energy, the r squared potential energy, gives you as its solution an ellipse. We didn't even have to work for it. Okay, it all fell into our lap just by writing down this elliptical problem right here. But I've taken a couple of liberties already. You'll notice I didn't write, here, let's do this a little more carefully. Minus integral a vector to r vector. And now we need that force minus m omega squared r, and then we would have had r over r, which is just a unit vector. Okay. If I didn't say it, I should have. This is just a unit vector, the vector divided by its magnitude. And we would have had to dot this into our dr. Okay. That being the case, these would have canceled, and the dot product of r dot dr turns into magnitude r times dr. Okay. Because this is away from the origin, and the other component of this vector is tangential, and its dot product would give us a 0, okay? So that's how you actually construct this. And this then turns into the magnitude R as well, because you can see yourself being on concentric circles. Okay, so that's how we go from here to here. And we've treated this central force problem without the actual central force, the complete central force formalism. Which is why I'm stressing this is not the Kepler ellipse, but it is an elliptical orbit for a quadratic potential, Hookean potential energy. This is a Hooke's law form. We consult the clock. I think that's a good place to stop. Yeah, I'll just add a note or two and then we'll call it a day here. We'll send this up. Yeah, so like I said, that's just the unit vector. There's the magnitude. We're going to be spending a lot of time with these types of expressions and their gradients and so forth. You know, I'm going to add one more interesting problem as a homework. Namely, we should start doing some of these gradients and curls just for practice. Go ahead and erase this side here. You know, when we're working with central forces, we have F is equal to F of R, and has more specifically the F of R times a unit vector. This is more general than this. This is the particular central force formula. This is function as a function of position, but this is the one that's the actual central force. This form here. So we should, of course, have and we know that F is equal to minus the gradient of U, but for a central force, U is the potential not of the argument's not the vector, it's the magnitude. Okay. So homework, take these derivatives, show that gradient U of R is equal to minus this thing here, F of R, R over R. And the way you do that, maybe I'll just do it for you, because we have d U of R dx, right? We're going to have three of these for the gradient, dx, dy, and dz. So let's just do it for x. That's going to be, U prime of R times d R dx equals U prime of R. Now what's this dr dx? That's d dx of this square root, x squared plus y squared plus z squared. Just carrying the U prime of R with me. I should have probably just worked this derivative, but that's okay. So what do we have here for this derivative? 1/2 root in the denominator Well, now the power of the inner derivative is 2x, and I'll wrap this up like this. Wrap this up like this. The 2's cancel, so that's u prime of x, and then this here is x over r. So if I do all three of them, it's going to be gradient u of r is u prime of r vector r over r. Okay. So that gradient u prime of r vector r divided by r. I'll leave it at that. So I've actually shown half of this problem, and the other half is just formally showing that u prime of r is equal to minus f, and then you're done. Okay. But yeah, this is a really key one for us to understand. Good. I'll leave it at that, and see you guys next time.